is the Clark refractor. It's a telescope. It's 10 meters long. It's got a lens this big. Okay, and you can look through it every night. For 100 years, people have been looking through it, and they haven't seen one, not one, alien spacecraft. Okay, zero, goose egg, nada. Okay, every night people look through it. They take pictures and pictures and pictures. And do they see one alien spacecraft? No. So that doesn't mean they're not aliens. There's got to be aliens, okay, because there are 50 billion galaxies. Each galaxy has what? That old saying, billions and billions of stars. But to say that aliens come here and cut open cows, take people up into their spaceship, hypnotize them, and nobody notices with this thing, I mean, it's just not extraordinary proof, okay? Extraordinary claim, aliens come here, extraordinary proof. Boy, we don't have it. This is the real science. This is what's really cool. Did you know that the Earth goes around the sun and the moon goes around the Earth in a very predictable cycle? Very predictable. See, the moon is always the same. It never changes. It's the same size and shape, round like a ball. But it looks different to us here on Earth because of the way sunlight hits it. That's right. Moonlight is really sunlight. And it changes because the moon is going around the Earth, and the Earth is going around the sun. Everything's just going around. Okay, let's say that this baseball diamond is the orbit of the moon. Now, the diamond's square and the orbit's round, but you get the idea. Now we need a sun. So let's say that the Earth is on the pitcher's mound. Now see, by the way, the scale of this globe and this moon are about right with respect to the orbit of the moon. That's the baseball diamond. Now notice that right now, when you're standing on the Earth, you can't see the moon at all. This is what we call a new moon. And the reason you can't see it is the moon is between you and the sun. Now the moon orbits the Earth in this direction. So when the moon gets to first base, it's a half moon because sunlight is falling on half of it. Huh? Then it keeps running to second. Now when the moon's back here at second, it's a full moon. That's because the moon is on this side of the Earth. And here's a trick. The moon's orbit isn't flat. It's tilted. So a lot of times, when the moon's back here, will be way up here. But notice it's still a full moon. And this is why most of the time the Earth's shadow doesn't fall on the moon. It's almost always full. Got to keep moving. On to third. So over here at third, it's a half moon again. But look, the shadow's on the other side. That's because we're on the other side of the Earth. Well, time to break for home. So with the orbit set up like this, the moon would end up right on home plate. The moon scores a home run every month. Well, that's astronomy for you. Electricity is the flow of electrons. Electrons are the tiny particles that buzz around the outside of atoms. Now, when electrons are able to jump from one atom to another, well, that's the flow of electricity. Now, in some materials, like metals, electrons can jump from atom to atom very easily. This plug fits in this socket perfectly, but this plug is from Europe, and it doesn't fit in our sockets. No way. See, different countries use different style plugs for their electricity, but notice that they all have two prongs. That's because electricity has to flow in a loop. So it goes in one prong through this wire, through an appliance like this blender, then out the other side and back into the wall. It's a circuit. Between where I'm standing and wherever you're sitting, there are millions of different types of plants and animals, millions of different species, all living together in an environment in something we call an ecosystem. Now, in order for an ecosystem to be successful, in order for it to be healthy, it has to have different kinds of plants and animals. Lots of different kinds of plants and animals. Something we call biodiversity. Now, biodiversity sounds kind of complicated, But if you listen, it also sounds kind of nice. This is the Earth, our world. All the living things that we know of live here, and they live in ecosystems. Places like tundras, taigas, savannas, grasslands, prairies, deserts, steppes, intertidal zones, subtidal zones, continental shelves, deep ocean zones, estuaries, deciduous forests, temperate rainforests, tropical rainforests, Arctic ice packs, wetlands, marine mudflats, and cities. That's a lot of environments, but there are a lot of living things to fill them up. The Earth's environments are just crowded with life. Living things take hold everywhere they can. We can think of an ecosystem as this wooden puzzle game. See all the different species? They all fit together, and they depend on each other to live. Now, you know, once in a while, a species will go extinct. It'll disappear from the ecosystem. And you can see how you could lose a few of those without too much trouble. But if you start to lose too many, the whole thing becomes a little rickety. Now, where do people fit in? Well, look, they fit in just about everywhere. Look, just about anywhere you can walk, you'll find people living, because people are living things, and they're part of the ecosystem. So, when we go to manage an ecosystem, we have to be careful about how things fit together, or there won't be a place for us. We have to be very careful. Extremely careful. The moon doesn't just sit up in the sky either. Its gravity pulls on everything on Earth, including the ocean. So see this? This is the high tide mark. And way over there is the low tide mark. Now, along with the sun's gravity, the moon's gravity makes the ocean move from there to here every day because of the pull of the moon's gravity. Now, what's the main reason we have tides? Because there's a moon. Energy can make things change phase. Like, this burner is providing energy that makes this liquid water change to water vapor. It's changing phase from a liquid to a gas. Now, watch this. This is liquid nitrogen, and it's going to change phase too. I'm going to pour it into this flask, and it's changing from a liquid to a gas without the help of a burner. It doesn't need it. That's because it's so cold, minus 196 degrees Celsius, that the energy in the room is able to make it boil. This stuff looks kind of dangerous, doesn't it? But it's nitrogen. It's the same gas that's between you and the television. 78% of our air is nitrogen. So, the heat from the room makes the molecules move faster and faster, and they get farther and farther apart. And they change from a liquid to a gas. Now, what happens when molecules slow down? Well, they get closer and closer together, and some unusual things can happen. Here, let's try something. We'll take this, it's a rubber ball, this, ordinary onion, and a few of these, marshmallows. And we'll put them in liquid nitrogen and let them cook for a while. Come back in a couple minutes and we'll see what we get. If you just joined us, we've been cooking with liquid nitrogen. Liquid nitrogen is minus 196 degrees Celsius. It makes molecules slow down and get closer together. Here, watch. It's an ordinary rubber ball. Here's an onion. Oops. Liquid nitrogen gives you an unusual way to slice it. Astrology started out as the study of the motions of stars and planets. Most astrologers take it a step farther than that. They claim they can tell a lot about a person's personality just by knowing when you were born. Now, that's a claim that's pretty hard to prove. Now, 2,000 years ago, astrologers believed that the Earth was at the center of everything, and the stars and planets were attached to a big dome or sphere. They used names for groups of stars, and we still call them constellations. This one is supposed to be fish. Now, if we could go way out in space and look at the same group of stars, like this, well, we wouldn't see a fish anymore. Anyway, It is interesting to note that the gravitational pull of all the stars in this constellation is way less than a trillionth of the gravitational pull between you and the television set you're watching right now. Does that mean astrology is wrong? Well, astrologers make claims that can't be proven or disproven. They're vague, they're wishy-washy. Now, that's not science. It's, well, you decide. How do we know that atoms combine to make molecules? This is H2O. Water. 2 parts hydrogen and 1 part oxygen. When the atoms come together, they stick. Okay, but how do we know? Well, take a look at this. In here, we have some water. And we're passing electricity through it. When we do, we get 2 gases. If we let it go long enough, there'll be no liquid left at all, just the gases. And they're pure. They're each made of just 1 kind of element. On top of that, there's twice as much of this gas as this gas. By doing a lot of experiments like this, scientists have figured out that, H2O is 2 parts hydrogen and 1 part oxygen, with the hydrogens on one side and the oxygen on the other. Kind of like mouse ears. See? H2O is great. The ocean is made of H2O. You and I are full of H2O. It's wild. It's wonderful. It's water. Almost everywhere you go in space, there's nothing. It's empty. There's zero, nada, zilch, zip. That's because space is a vacuum. It's a void. It's almost devoid of everything. That's why astronauts have to wear spacesuits. Take a look at this. It's our vacuum of space, vacuum chamber of emptiness, of space, of science. And this is cherry soda. Soda has gas in it. You've seen the bubbles. Well, your blood has gas in it too, like oxygen and nitrogen we get from the air we breathe. Now watch what happens when we put the cherry soda in a vacuum. As we take the air out of the chamber, there's no air above the liquid to hold in the bubbles. So the gas comes out of the soda. You see, the same thing would happen to you in space if you were in the vacuum without a spacesuit on. That's why astronaut spacesuits and spaceships have to be airtight, or human bodies wouldn't work. Look at that. This would be like your blood in space, and it would be boiling in the vacuum of space. A is for atom. That's right. A is for atom, because atoms are the basic building blocks of all matter. Atoms are like the letters in the alphabet of the universe. So look what happens when we combine these letters. We get words. Atoms are like letters, and molecules are like words in our universal alphabet. All matter is made of atoms and molecules.
Hey, science guy.
Huh?
Even a banana cream pie?
Oh, yeah. Even a banana cream pie. Our eyes are connected to our brains by big, complicated bundles of nerves. The nerves are so big and complicated that many scientists like to think of our eyes as part of our brains. See? And here is the eyeball. That's right. Your eye is shaped like a ball. And inside is the lens. The lens is the clear part that light goes through. And in your eye, the lens sits way up near the front, like this. Now, before light gets into your lens, we have to control the amount of light that comes into our eye. We don't have too much or too little. And we do that with something called the iris. The iris changes size, like this. By the way, the iris is the part of your eye that has color. Like someone says to you, you have blue eyes, or brown eyes, or green eyes. That's the iris, this part right here. Now let's say we're looking at something, maybe a kid on a stick out here. All right, the light from the kid on a stick goes through our iris, through the lens, to the back of our eye. And look, the image of the kid on the stick
is upside down. Isn't that wild? The kid on the stick is upside down.
We heard you, Bill.
So our brains take the upside down images from both our eyes, turn them right side up, mix them together, and make sense out of what we see. The same thing that makes this happen makes this happen. And this. It's electricity. Whoa. Well, electricity is the flow of tiny particles called electrons. And they're not just smaller than atoms, they're actually part of atoms. Take a look at this. It's our battery-powered electrical circuit of science. We're going to run this big light with this big battery. Watch.
Attention, the Nilab.
See, right now, electrons can flow from this side of the battery, through this wire, through the switch, through this wire, into the light, and back to this side of the battery. They're flowing in a closed path, what scientists call an electrical circuit. Now, circuit, that's from an old word for go around. So electrons, right now, can go around an electrical circuit. The flow of electrons is a lot like the flow of water. No kidding. Watch. When I operate this great big water pump of science, water goes through this hose into this box and makes this water wheel go around. And it goes out the other side and through this hose back to the pump. It's a closed path for the flow of water. It's a water circuit. It's just like the flow of electrons through an electrical circuit. Electricity is a very versatile form of energy. The same electrons that are making the light up are making a motor go around. See, electricity can do all kinds of different jobs, and they're all done with electrons.
Whoa, dude. This is awesome.
Definitely. Awesome. I mean, like all those stars. Dude. Oh, there's millions of them.
And like each one of those stars is like a sun.
Like, whoa. Dude. That means that, like, oh, there's tons of other solar systems.
Well, yeah.
Whoa. And that means that we're like little specks. Oh, like almost nothing.
Whoa.
Now, one of the coolest things about dinosaurs is that of all the millions and millions of dinosaurs that must have once lived, we only know about a few thousand. And we know about them because we found their bones. They're fossil bones. Now, fossil, that's Latin for something that's been dug up. So we've dug up dinosaur bones. That's how we know how big they were, how much they weighed, what they ate, even how fast they could run. Now, we don't know all about dinosaurs, but we do know a lot. Now, let's say you're a dinosaur, a Potosaurus. Yeah, Potosaurus. And you were walking along, minding your own business, and there was a flood. Oh, no. And you got buried very quickly. You drowned, and silt and mud washed down over your bones and covered you up. Then over time, minerals worked their way into the little gaps in your bones. Your bones became permineralized. Minerals all the way through. Okay, and you sat there for 65 million years! Then, about 100 years ago, a paleontologist comes along. This would be Mary. Looking carefully, maybe poking around. She goes, oh, what's this? And she very carefully brushes away the sand and dirt that you've been buried in. And, oh, look, an Apatosaurus. Yeah, Apatosaurus. Quite a wild time for a dinosaur. Did you know that white light is a mixture of all the colors of the rainbow? It is. Now this is the plastic water-filled prism of science. And shining into it is a bright white light. Now when white light goes into a prism, it breaks up into all the colors of the rainbow, what we call the full spectrum of colors. So down here is the spectrum being made by the prism of science. See, here are all the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and purple or violet. Now watch. I'm going to try to break these colors up using another prism. Red, yellow, green, blue, and violet. See, they can't be broken up anymore. What that means is these are pure colors. White light is a mixture of all the colors of the spectrum, but each color is its own color. White light is colorful.
About 2,000 years ago, in the town of Alexandria, which is here, near the mouth of the Nile River, what is now Egypt, there was a guy named Eratosthenes, and he was the librarian of the great Library of Alexandria. One day, he came across a note from someone who lived here in the town of Sina, and the note said, "At noon on the longest day of the year, Styx cast no shadow, and we can see all the way to the bottom of our wells." Eratosthenes realized that where he lived, Styx did cast a shadow, and he couldn't see to the bottom of wells. And he got to thinking about it, and he realized, oh, the earth must be round. Yeah, we must be living on a big ball. That's the only way for there to be no shadow here and a shadow here. So he measured the shadow that the stick cast, and then he paid someone to walk from Alexandria to Sina and keep track of the distance as carefully as he could. Well, that distance turned out to be around 800 kilometers, and the shadow was about a 50th of a circle. So then he multiplied 50 times 800, and he got 40,000 kilometers, and that's the distance around the Earth, what we call the circumference of the Earth. So check this out. This guy made observations of a star, our sun, and he figured out the size of a planet, our Earth. The same kind of observations that you can make. Hey, not bad.
What makes one atom different from another?
The number of protons in the nucleus?
The number of protons in the nucleus. Take a look at this piece of metal. It's shiny, like silver. Now here's another piece of metal. It's shiny too, but it's a little bit orange colored, like gold. Now this material turns out to be aluminum, and this material turns out to be copper. Now the main difference between this material and this material is
The number of protons in the nucleus?
the number of protons in the nucleus. You can see and hear the differences.
Bill! Hey!
Now, scientists have grouped all the different materials, all the different elements that we can find into groups, which have come to be called periods. And we've arranged the periods on a table, the periodic table. So let's go to the chart.
The periodic table.
The table.
Yeah.
The periodic table.
Uh-huh.
Voila! The periodic table. See, every element has a name, and you know most of them. They're familiar. There's carbon, oxygen, aluminum, copper, iron. They're familiar. But there's some weird ones too. There's like erbium, palladium, and krypton. Scientists have given each element a 1 or 2 letter symbol and a number. Now, that's not just any number, that's the atomic number.
The number of protons in the nucleus?
The number of protons in each nucleus. Now, there are 92 elements that occur naturally. And using these elements, we can make all kinds of interesting molecules. How did life get started on Earth? Where did evolution begin? Well, near as we can figure, the ancient Earth was covered with the ocean a little over 3 billion years ago. And the ocean was a sort of primordial soup that living things got started in. Now, primordial, that's an old word that means very old. See, scientists have done a famous experiment with primordial soup where we cook it. The experiment would look something like this. Put primordial soup in a big flask, cover it with what we believe to be the ancient Earth's atmosphere, which would be ammonia. And ammonia is the same stuff you smell when you clean a window. We cook it by heat from the sun, and this would be freshwater rain, which would come out of this boiling flask right here, and lightning from primordial thunderstorms. The thunderstorms make the molecules change and rearrange themselves. And eventually, we have found that we can reproduce tiny pieces of deoxyribonucleic acid, tiny pieces of DNA.
DNA,
The very building blocks of life
the blueprint for future generations.
can be made with an experiment somewhat like this one. So the primordial soup was very much like the ocean is today. Look at all these living things. The ocean's full of them. You and I are living things. The primordial soup is still cooking.
Living things evolve, living things change, but not that fast. Now here's a dam that humans put here, and over here is a fish ladder. And here's the idea. Fish can swim from step to step and get up the ladder and get up past the dam. Do you see what I'm saying? But do you see one fish? One big salmon over there? I mean, salmon are big. You see one? Not one. I mean, salmon are like this. You think I'm telling you fish are? They're big fish. If they were over there, you'd notice them. And some people say the sea lions are eating them. Well, the sea lions might eat a few fish. Maybe they eat a lot of fish. But they don't eat this many fish. I mean, it's a lot of fish that aren't getting past the dam. They aren't getting up to this fish ladder because humans have changed their environment. Humans have let silt come downstream, chemicals get in the water, they dam the stream up altogether so the salmon can't swim past. And you know what else? It's not one person, millions and millions of humans slowly degrading the streams, made the environment not so good. So you got no salmon. You know what I'm saying? Because humans have changed the environment. Now, a fish could adapt. It could evolve, but it would take millions and millions of years. It's not going to happen in 100 years. It's not going to happen in a weekend. It takes a long time. Humans have changed the environment faster than most living things can keep up.
Oh, great. Science! Thank you all. It's so good to see you. Unlike, I believe, all of my colleagues, I am an engineer. I mean, let me emphasize, like my colleagues, I'm a human, but engineer. So my older brother, tremendous influence on me, had a wonderful physics teacher, Woodrow Wilson High School, Washington, D.C. And he told my brother the story, who told me the story. Michael Faraday, in 1828, then through 1831, would do the Christmas lectures in London, which is back east someplace. And he did this demonstration where he had a coil of wire on one end of a laboratory bench connected to another coil of wire by two wires, the terminal wires of the coils. So he goes down here with a bar magnet, reasonably powerful magnet, which you could find in those days. So he moves the magnet at this end of the table, and the compass needle moves at this end, as if by magic. Of course, it wasn't magic, it was science! Yes. So the story was embellished. And it was presented to me that he did this demonstration with such success so often that he presented it to the Queen of England. And the Queen of England is supposed to have said to him, Mr. Faraday, of what use is it? And here's where I just admire the guy, and I admire what we in the United States perceive as the British way of thinking. He did not say, lady! What? Are you, would you look? That's at that end, I'm at this, I'm not touching it. What? Are you high? I mean, come on.
I love it. Your eyes are awesome.
But that's not what he said. According to the story, he said, Madam, of what use is a newborn babe? Now, I don't know how much time you have spent with newborn babes, but they're not that useful. They're loud, and they leak, and there's a lot of times they don't seem to understand a word you say to them. Look around, everybody. Everything in this room, everything, the lights, the curtains, the paint, the clothes you're wearing, the upholstery, the floor, the stage, everything here owes its existence to that discovery. To the discovery that not only is there a connection between electricity and magnetism, but there's a connection between electricity and the moving of the magnetism, the flux. And that discovery, dare I say it, changed the world. But this process of science that this guy spent, I guess, he took tremendous pride in his demonstrations, and he really perfected this to show it to people. This discovery had a deep effect on me. Now, when I was a kid, I delivered the newspaper. I was a paper boy. That was the title. And in the Washington Post on Sundays, there'd be Ripley's Believe It or Not. And it's still there. It's a different paper, but still there. And it would say from time to time, they would run the story roughly, according to aerodynamic theory, bumblebees cannot fly. And this made quite an impression on me. And I spent some time watching bumblebees. And it became clear to me that the bees are fine. The problem is with the theory. And then I realized that I could influence objects. I realized that if you could understand things enough, you could make things and shape things and imagine traveling around the world. And you could do it with a balsa wood airplane. Just think what you could do if you worked for a big company like Boeing. And that's what I ended up doing. I worked on 747s. Relax, everybody. I was very well supervised. But these things that happen to you when you're a little kid influence you so much. And I'll bet you everybody in here who's a science enthusiast got excited about it before you were 10 years old. And this passion, this drive to know our place in the universe is what makes us special. It's what makes our species worthy. And with this PB&J, this passion, beauty, and joy, we can, dare I say it, change the world. Thank you.
Extraordinary claim, aliens come here, extraordinary proof. We don't have it. This is the real science. This is what's really cool. Did you know that the Earth goes around the sun and the moon goes around the Earth in a very predictable cycle? Very predictable. See, the moon is always the same. It never changes. It's the same size and shape, round like a ball. But it looks different to us here on Earth because of the way sunlight hits it. That's right, moonlight is really sunlight. And it changes because the moon is going around the Earth and the Earth is going around the sun. Everything's just going around. Okay, let's say that this baseball diamond is the orbit of the moon. Now, the diamond's square and the orbit's round, but you get the idea. Now we need a sun. So let's say that the flow of electrons. Electrons are the tiny particles that buzz around the outside of atoms. Now when electrons are able to jump from one atom to another, well, that's the flow of electricity. Now in some materials, like metals, electrons can jump from atom to atom very easily. This plug fits in this socket perfectly. But this plug is from Europe, and it doesn't fit in our sockets. No way. See, different countries use different style plugs for their electricity. But notice that they all have two prongs. That's because electricity has to flow in a loop. So it goes in one prong through this wire, through an appliance like this blender, then out the other side and back into the wall. It's a circuit. Between where I'm standing and wherever you're sitting, there are millions of different types of plants and animals, millions of different species, all living together in an This is the Clark refractor. It's a telescope. It's 10 meters long. It's got a lens this big, okay? And you can look through it every night. For 100 years, people have been looking through it. And they haven't seen one, not one alien spacecraft, okay? Zero, goose egg, nada, okay? Every night people look through, they take pictures and pictures and pictures. And do they see one alien spacecraft? No! So that doesn't mean they're not aliens. There's got to be aliens, okay, because there are 50 billion galaxies. Each galaxy has what? That old saying, billions and billions of stars. But to say that aliens come here and cut open cows, take people up into their spaceship, hypnotize them, and nobody notices with this thing, I mean, it's just not extraordinary proof, okay? So a lot of times, when the moon's back here, we'll be way up here. But notice it's still a full moon. And this is why most of the time, the Earth's shadow doesn't fall on the moon. It's almost always full. Got to keep moving. On to third. So over here at third, it's a half moon again. But look, the shadow's on the other side. That's because we're on the other side of the Earth. Well, time to break for home. So with the orbit set up like this, the moon would end up right on home plate. The moon scores a home run every month. Well, that's astronomy for you. Electricity is the Earth is on the pitcher's mound. Now see, by the way, the scale of this globe and this moon are about right with respect to the orbit of the moon. That's the baseball diamond. Now notice that right now, when you're standing on the Earth, you can't see the moon at all. This is what we call a new moon. And the reason you can't see it is the moon is between you and the sun. Now the moon orbits the Earth in this direction. So when the moon gets to first base, it's a half moon because sunlight is falling on half of it. Huh? Then it keeps running to second. Now when the moon's back here at second, it's a full moon. That's because the moon is on this side of the Earth. And here's a trick. The moon's orbit isn't flat. It's tilted.